the assembly job. So that is the work that we proposed in this. So quickly going through this. So this was 3D printed. You can see like this. The different discs were there which were assembled together, and this is some printing going on. And finally, we were able to get the output in the form of a electrical output in the form of 1.5 volt. So once we assembled this system, actually we did not get the voltage immediately. We were really disheartened, like why this is not happening, because the theory says that if these all salts are put together, they are supposed to convert the chemical energy into the electrical output. So one of the probable reason was, since I am putting the ABS as a binder into this, it may have blocked, because it's an insulator, the flow of charge from one disk to another, right? So what we did is we took some acetone, and on the interface we have put some acetone drops, and suddenly we got immediately 1.5 volt, right? So we were really happy, and then we tried to explore the other properties like mechanical strength and all using some tensile coupons. And another important observation for the behavior was for its thermal property. So what we observed, the dry cell that we were making were able to work at very high temperature, up to 98 or 95 degree, whereas normal dry cell in which the polymer is not there can work up to 55 degree. Similarly, on the lower temperature, my normal dry cell may not work below room temperature, below 0 degrees Celsius temperature, whereas this can work very well up to minus 20 degrees Celsius temperature. So this we came to know about through the thermal analysis only in the different heating cooling cycle. So that is the another beauty of working with these type of reinforcement to get some smart behavior, right? Now coming to the actual 4D in the construction industry. So we use the concept of a parallel current carrying wire, carrying current in same direction and carrying current in the opposite direction. So what the idea is, so we printed some successive layers of material. This is the first layer, which is of an insulator. Then the green layer that we are seeing, this is a conductor. So what we actually did is we use the ABS plus graphene, we use the nylon plus graphene particles, right? So we made the alternative layers like this. Then we allowed through the microcontroller, we put the defined quantity of the charge, we allowed it to pass. So the current carrying wire carrying current in this direction, this is basically a DC. So we have a north-south over here. Then on the lower layer also there is a north and south. Now this north and south will attract each other, so there will be compaction. Then we change the direction of the current. So there was south and south, so there is a repulsion. So contraction, repulsion, contraction, repulsion. This is what simply a transducer. So we were able to print a transducer, right, using a simple concept of conducting and non-conducting layers. What is the typical application? The typical application is in this ultrasonic machining. As a typical mechanical engineer, when we used to talk about the ultrasonic machining process, it is having a some electric generator or electric power sources there. Then there is a transducer which converts the electrical energy into the mechanical vibration. These vibrations are amplified, and then through the tool, basically the ultrasonic vibrations are coming to the abrasive particles which are moving or flowing between the tool and the workpiece. Now these abrasive particles, when they strike with the tool, their momentum increases 1.5 lakh times. So with that high momentum, they strike with the workpiece and they basically erode the material, and finally the cavity is created. Now I have personally worked on this machine. This type of transducer for a machine like of Sonic Mill, which is US based machine, this costs us something around $80, whereas as my transducer is available as low as 20 rupees, because just I have to print some successive layers and I can basically control the the compaction and expansion, and basically control the amplitude of the vibration, right? So that is the one beauty, and we can make our own setup with this and can control some of the mechanical motion over here. Then as a typical process, what we actually did is we made a tool like this which has to be installed at this end, because we know that tool is not actually going to be in touch with the workpiece. So what actually we did is we use the concept of the broach. So in a typical broach, there are roughing teeth, semi finishing teeth, and the finishing teeth, right? So whenever I am ultrasonic drilling this part, so once the part is entered inside, now this zone, outside zone, this is having a coarse grains of the alumina. So once it enters inside, these abrasive grains are of relatively finer one, and once they move further, the more fine grains were there. So coarse grain, fine grains, and very fine grains. So ultrasonic drilling along with broaching. So this is something adding to the process, and we have the IPR for this also, and we can go for the simultaneously drilling or machining along with the uh, super finishing process. Okay, now some of the things that actually we can do for our 3D printing at very less cost is managing the Baru effect, specifically in the polymer material. In most of the 3D printing setups, I have a nozzle like this. Through this nozzle, my material is extruded, and the output part is something like ellipse. Now this change is because of the surface tension, and the effect is called the Baru effect. Now once the different layers are deposited, the layers looks like something like this. So in each successive layer, there is a gap, there is a air gap, and we may correlate it with a like a packing factor. And because of this air gap, the surface characteristics, surface finish, and the dimensional stability is compromised. Now, to overcome this problem, what we suggest is to use a nozzle like this. Now, this profile was cut on a brass nozzle using a EDM wire cut. But once we use the nozzle like this, we get a expanded shape, something like this. So these triangular layers were put over there. Then I have to make another layer. So through the stepper motor, the nozzle was shape was changed, and the second layers were of the inverted triangles. Then again in the next layer, again the rotation of the nozzle, right, and then the another way of putting the triangles, right. So this is the one of the smart way of reducing the packing factor, or getting the highly dense part, reducing the porosity. We got this idea from the Sony technology, right? Like for example, in mid 90s, there was a very famous brand of color television, that was Texla. And the idea of working in that particular television is, there is a silver screen, you have a gun, and through that gun basically we bombard the electrons over the silver screen. So once we bombard, we get a pixel over the surface where the electrons are striking, right. So those pixels were normally circular in nature, so different pixels coming together, and finally they made an image. But in mid 90s, this Sony people, they came up with a technology called Trintron, in which they basically manage the angle of impingement, the standoff distance, the speed of striking of the electrons, and the pixel size was controlled in such a way that the pixel was finally not of the circular shape but of the triangular shape, and finally those very sharp image as compared to the circular images were observed. So taking that thing in mind, the nozzle were altered. So you will be surprised to work over a single nozzle. It just costs you 10 to 15 rupees extra for getting a some profile cut through the EDM wire cut process, so that you can have a better surface characteristics. Now, similar to the previous case, the another advancement can be, if you want to use the parallel nozzle, then one nozzle can be of a circular shape, another nozzle can be some shape like star, and after the expansion is there, so this will be looking something like this. So parallel we can have a printing something like this. This will help us in reducing the the cost, specifically on the post finishing process. This is useful when I am using a two nozzle heads together. I have seen a machine with a 10 nozzle head together in IIT Bombay, in which some of the student project was going on, and they were working on the 10 nozzles together. Right? Is the idea clear? Any question till now? Any question till now? Yes, please.
No, sir.
Okay, very nice. I think the advancement part is little helpful to us, right? Okay, now coming next to it, the case study that I am presenting in front of you is on the 4D material that have been developed specifically for the structural application. This was one of the paper with my colleagues, which has gone maximum number of downloads 2 years back. Open access paper. This is available, and we got really good appreciation for this work, specifically in the area of the 4D. The idea is on the development of the 4D material for the heritage structures. Now, in our country, the heritage structures are divided into three categories. One is called grade 1 structure, another is called grade 2 structure, another is called grade 3 structures. So grade 1 structures are basically those structures which are under the control of government of India. Archaeological Survey of India people, they basically take care of those structures having a national international importance. And if you want to do some even a small change in that structure, you need to take permission from many sections. There is a lot of protocol involved in these type of structures. One of the example is the structure of the Taj Mahal, right? So you cannot put any foreign material into that structure. It should not distort. There is a clear cut mandate. You cannot add the foreign material into the structure without the permission at different ends. Lot of protocols are there. Then there is a grade 2 structure. The grade 2 structures are again the structures of national importance. Maybe through Archaeological Survey of India, the structures are managed, or through the state departments, right? So again, for the grade 2 structures, again the protocol is there. One of the basic point in the protocol is the foreign material for the maintenance of these type of structures should not be used. Only the material which is available at the time of its original making, that only you can use, right? So that is a big challenge in the maintenance of the grade 2 structures. Then there is a third category which is called the grade 3 structure, for which one picture I am showing in front of you. This is a grade 3 structure. These are basically the private properties which are again important from the heritage point of view, but we can definitely deliberate on the use of some foreign material and prove the uh, proof of concept, right? And if it is applicable in grade 3, then the allow government allows it for grade 2, and finally for the grade 1 structure. Now the picture that you are seeing in front of you is a grade 3 structure in the district Ludhiana of the Punjab state. This was built in the British period. And the what is the problem? Let me share. Let us say this is the heritage wall, and this side of the wall is accessible to me, and this side of the wall, which is we call it as the back side, is not accessible to me, and in between I have a crack, right? Then there is a second case in which the entry side of the crack is large and the rear side of the crack is small. Then there is a third case when the entry is small and the from the rear side this crack is a little large. Like for these three different cases, I need to have a different type of treatment. Like there is a company called Hilti, which is a multinational company, German based, which provide a epoxy solution for these type of the cracks, right? right? So what we do is for the crack propagated, we took a epoxy, we use heat, temperature, and the pressure, which basically pushes the material and fills the crack like this. But if the crack is of type 1 and type 2, as shown in figure A and B, this can be easily filled. But in the case of crack shown in the part C, it may not filled, specifically if the crack is propagating in upward direction or coming in the downward direction. So keeping all these things, we have to be develop a smart solution which can be there once it enters into the cavity. It takes the shape of the cavity. So that is something about 4D. And there is a very good journal of cultural heritage by elsewhere, which shows a lot of paper or the research work showing in this area, in which people have worked for the smart fillers for the these type of the structural cracks. So what is the idea of doing the work? First is the crack detection. So that is usually by laser scanning. Then we are interested in the volume of the cavity. So using a photography, I am interested in getting the X and Y. And for the depth Z, normally we use the radiography or the ultrasonography. So once I know X, Y, and Z, so I know the volume of the cavity. Then develop a thermoplastic reinforcement material, which once enters into the cavity, it is squeezed, right? And once it is there inside, it is expanded and it take the shape of the cavity. And finally, we are able to have a smart assembly of this type of the material. So that is the work that I want to show to you. I like to have other structures over which this has a lot of application. Like you see, in case of these bridges which are constructed over the, of course, in the British period itself. If you see this, there is a arch structure. Now in this arch structure, on this lower axis there is compressive load, and on this axis there is tensile load. But I am using a same composite material with a similar compressive and tensile properties, right? So I need to have a smart material where the layer which is under the compressive load, it should place like this, and the upper layer where there should be a tensile load, it should place on the top. Then on the downside, this is the actual field. This is a grade 2 structure. This the name of this structure is Sarai Lashkari Khan. This was built in 15th century by a Mughal general, and his name was Lashkari Khan. And the Mughal Emperor Aurangzeb period was there, and their army basically moves from Lahore side to the Delhi side, and they have a halt in this Sarai Lashkari Khan, which was near on the, of course, national highway from Amritsar to Delhi. And this is something near, there is a small town called Duraha near to Ludhiana, where this structure is actually already there, and we are in the preservation of this type of structures. One of the basic challenges, like for this structure, there is no use of the cement, right? So because in 15th century we were not aware about how the cement manufacturing is there. So people are using crude form of cement, right? So what is the crude form of cement? Like a limestone. Because in cement manufacturing we only came to know in the 19th century, where I was known that if I want to make a cement, I have to heat the calcium carbonate up to 1300 or the 1400 degrees Celsius. Then there will be calcium oxide plus CO2. CO2 will go to the atmosphere. Calcium oxide with alumina, this will make clinker, and I will be able to make a cement. Now if I take the present day cement to fill some of the cracks, so there will not be a bond formation, there will be a poor bond formation. And as per the archaeological survey guidelines and the CPWD guidelines, I cannot put the foreign material with a very poor bonding capability to bind with this type of material. So the only solution that left with me is developing a material from the debris itself, and then do the assembly of these type of parts. Now to have a proof of concept, we used three different material. One was HIPS, another was ABS, and third was PLA. So if you see the MFI of HIPS, the observed value was 7.5. For the ABS, it was 8.7, and for the PLA it was 13. One simple understanding from this data is, if the material is having a high MFI, that means I can make the thin section out of it. If it is having a lower MFI, I cannot make a thin section, I have to make a thick section. Now just imagine I am printing a complex shape with a functionally graded material, and the flowability is challenging, then how I will be able to make. Then the young modulus was calculated. This was 112 for hips, 175 for ABS. The grade we selected, and 47 for the PLA, so the lowest one. Similarly, there is a wide difference in the other mechanical property like gross transition temperature, peak load, peak strength, peak elongation. Then we have a observed value, standard deviation, standard error calculation with respect to this type of the material. Then what we did is we use a some fixed parameter of the fuse deposition modeling or fuse filament fabrication, like the dia of the nozzle was fixed, dia of the filament, layer height, default printing layers 3 up and down, filling pattern rectilinear, printing speed, travel speed, extrusion temperature, print bed temperature. All these things were kept constant, and we were able to have a different material combination like APH, PHA, HAP. APS means the ABS lower, PLA middle, hips on the top. Similarly, PLA lower, hips middle, ABS on the top. So, and all the different 9 combinations that are possible, we try to make the component by those things, right? So this is the view of making these type of the multi-layer components, and you can see the stress strain curve for a single material, and under the area under the curve, typically I can express the modulus of toughness, and we can calculate the Young modulus of this curve. Then the thermal analysis like that of the previous one, and now you see for the selected DOE, I have a wide range of area under the curves. Now, if I see the morphology of this we captured at 30x magnification using a simple optical microscope, right? If you see for a single material at 30x ABS, there is a layer by layer formation. Here again for the PLA, layer by layer formation, no side flow of material. For the hips also, there is a effect of raster, and you can see there is a continuous flow of material layer by layer. Then if I see the experiment number 1, the ABS was put first, followed by PLA, followed by hips. So once I put the PLA over the ABS, what happens? The side globule formation was observed. That means once I print the ABS and then I print the PLA, the material will have a side flow, right? Now, if you see the experiment number 4, once the PLA was down, then hips and then ABS, there was no side flow. Now, if I just compare it with this graph, in case 1, this was the area under the curve, and in case 4, this was area under the curve, right? So similarly with other things, what we came to know, which material we should print first, which material we should print later, so that I can have a better control of the flow properties, and these were very much in line with the mechanical properties. Now, keeping these things in mind, we can actually tune the printing of the material. We can actually tune the crystallinity. We can actually tune the glass transition. We can plan the other thermal properties so that best combination can be made. Now, this is the another case study for this. Before I conclude my talk, in this particular case study, we have used the dual thermoplastic material, and we were interested to explore what is the effect on the tensile, flexural, and fracture surface investigations. So we tried to make the component using the different grades of ASTM codes for the tensile and flexural. Now you can see in this case, this is a flexural loading condition and the tensile loading condition. The coupons were printed, and we use in this case to have a proof of concept 2 different material. One was ABS, another was PLA. We use some fixed parameters like bed temperature was fixed, nozzle temperature was fixed, infill percentage was fixed, infill speed was fixed, infill number of perimeters means outer layers, 2 perimeters were fixed, raster angle was fixed, layer width, number of layers were fixed as 6. So what we actually varied was in first experiment, all layers were of a single material called PLA. So you can see first PLA layer, second PLA, third PLA, fourth, fifth, sixth, all layers were of the PLA. Then in the second case, all layers were for the ABS. Then we use the concept of the random number, and from 3 to 12, some at random combinations like PA, PP, AP, this combination was printed. Now, what does this means? First layer of PLA, second layer of ABS, फिर two successive layer of PLA, फिर ABS, फिर PLA. So this was, tried at random. So what we observed, the failure pattern for the tensile and flexural coupon, they followed a specific path. This is the printed coupon. These are the observed peak load, peak elongation, break load, break elongation, peak strength, break strength, and the modulus of toughness. So this is the typical stress strain curve. Now, what we observed that the pattern follows failure pattern follows a particular trend, right? So we try to give the some name to these type of trends. So we introduce a terminology called number of conversions and number of negative conversions. Like, what is conversion means? Conversion from one layer material to the another layer material. So conversion was zero. What is number of negative conversion? Number of negative conversion is like if you are putting a material of high TG on the lower side and the lower TG on the upper side. So what will happen once you print like that? So the material with a lower TG will have a side flow. So that actually we observed in case of once we put a PLA on the ABS, because ABS is having a higher TG as compared to PLA. So if you print the ABS first and once you are putting the PLA, so there is a side flow of material. Now to have a proof of concept, let us take the example for the serial number A, serial number 6, A to P one conversion, P to A second conversion, A to A no conversion, A to P three conversion, P to A four conversion. So number of conversions were four. How many are negative? You can see A to P one negative, here another A to P two negative, right? So how many P's? There were two P's and four A's. What we observed, for the strength to be maximum, number of negative conversion should be minimum, followed by number of conversion, followed by number of P's, and followed by number of A. We registered this as our thumb rule, and this was printed, and we try to correlate with its thermal properties and other mechanical properties in terms like the flexural strength. So we observed a particular trend for these type of smart materials. So in other words, if you want to tune the property, like specifically like the metastructure part also, you can do that and can play with the different type of the properties. I believe this is well understood at your level. I will be happy to answer some of the queries if you want at this moment. Yes, now I am open for any discussion. Yes, please.
Good afternoon, sir.
Yes, please.
Sir, requesting you kindly explain more about the dry cell property that in place of MnO2, what you are adding so that the voltage is maintaining to 1.5 volt.
I am putting MnO2 only, but the difference is it is consisting of the four zones. So MnO2 part was consuming, so I am making it replaceable. So that disk was like a C washer, right, on a common graphite link. So only MnO2 salt part was consuming. So again, crushing that disk, making it powder, refilling with the more MnO2, and then assembly.
And the voltage is maintaining for a long time or for a short duration?
That depends upon the load. So like for the normal dry cell, you are getting the output voltage at 1.5 volt depending upon the load you put on it.
Okay.
So it will be giving a similar behavior, but only the difference is you are having a protective shell which can make it workable for high temperature or the low temperature application.
Okay. Okay, sir. Thank you so much.
Yes, anybody else? Please. You can mute yourself, unmute yourself, and ask the question. Yes, from the participants, physical participants. Anybody? From online participants, are you able to listen? If anybody has any query, please tell me. Offline. Okay. Ma'am, can you please? Thanks, sir.
Thank you, sir. Thank you very much for this informative lecture. Thanks a lot, sir.
Okay, thank you very much from my side. If you still further have some query, you can write a mail to me. I would like to answer the queries.
Okay, sir. Thank you very much.
Thank you, sir.
Thank you, one and all.
Okay. For the participants, we will meet you tomorrow at 9:30 for the next session. Thank you. Thank you, sir. Leave, Kamsa.